Okay, hi everyone. We have another physics problem to solve. So we're given a ring of charge, just a ring with charge Q uniformly distributed on it. And it's got a, basically linear, this is a linear charge density, uniform, say linear, linear charge density lambda on a thin ring of radius r. Find the electric field at this point P right here, okay? So how do we approach this? Now, we know from Coulomb's law that for a point charge, Q, or capital Q, doesn't matter, the electric field at distance r away is K Q over r squared. But we do not have a point charge here. We have a ring of charge. The charge Q is distributed on the surface of the ring. It's a very thin ring, like a thin wire. So how do we approach this problem? Using this as basis. Well, the first thing we do is we break up the ring into small little charges. So of course, this is an exaggeration right here, but this is a small little charge of length dl, some kind of a length, and charge dq. dq is differential charge or infinitesimal charge. Now this dq is going to have an effect at point P, and it's going to produce some kind of an electric field. Again, we're going to call it dE, which is an infinitesimal electric field from this infinitesimal point charge or charge distribution here of length dl. Okay? And this is all right here. So what is this element electric field or this infinitesimal electric field? Well, again, the electric field came from dq, so the electric field is K, the charge that gave it, over the distance squared. And the distance here is r. Okay? Similar in form to this one. These two are similar in form. All right, let's work some more. Now, what is dq? Okay, I'm given the total charge to be q, but not this little dq. Well, we know that, uniform charge distribution, lambda is the linear charge density, which means total charge q for this problem, the element dq, right, the amount of little charge is the density times the little length. Okay, so let's put that back in there. And this is the magnitude of the electric field. But we know the electric field is actually a vector, right? And this is its magnitude. If you look at this here, let's look at the electric field by itself. So this is the electric field pointing this way. And it's making some angle alpha with the vertical right here. So this electric field has some kind of component to the right. We're going to call it dE, horizontal. And it's going to have a vertical component, dE vertical. Okay. And dE vertical is dE cosine alpha, and dE horizontal is dE sine alpha. Okay, so what we need to do now is break up dE into vertical and horizontal components, and then add all the contributions or the vertical contributions, because again, this is just one element, right? I can choose another element here. Maybe put white on here. Here we go. This element is going to produce a similar DE with its own vertical and horizontal component. And another element here will produce another DE with its own vertical and horizontal components, and so on and so forth. So what do? How do we add vectors? We break them up into their X and Y components, in this case, horizontal and vertical components, add and subtract all the verticals together, add and subtract all the horizontals together until we have one vertical and one horizontal at the end. And from that, we reconstruct the magnitude and direction of the net or total electric field. Okay, so that's what we have to do here. But this problem possesses some kind of symmetry. Let's look at it. It's a ring, and I'm right above the center of the ring. Okay, see, maybe I should have mentioned that in there, but it's right above the center, not just at any point. Maybe I'll change it right above the, yeah, along the axis of the ring. I will reword this, but since it's along the axis of the ring, if this is my DQ, I have a DQ across the diameter from it. Take a diameter, go across the other side. I have another DQ right here. Same thing, with the same infinitesimal length and the same infinitesimal charge. So here I have DQ and DL. That is going to produce its own electric field at point P. So let's look at it. So this is the electric field from the DQ on the left, this one, right here. Now I want to draw in white the electric field from this DQ here on the right, okay? So it's going to be, again, coming up like this. Also making an angle alpha because of the symmetry of the problem. And when I break it up, I'm going to get here DE horizontal, and right here DE vertical. And for every DQ, for this one right here, across the diameter, along the diameter through the center, I have another DQ here that's going to have similar configuration for the electric fields. And if we look at this, we know just from the symmetry, the horizontal components will cancel out, because these two electric fields have the same magnitude, which is K lambda DL over R squared. The distance from the element charge to the point P is the same. From any point on the ring to the point P is the same. I'm taking the same amount of infinitesimal charge over an infinitesimal length. So the electric field has to be the same in magnitude. However, when I put them together, their horizontal components cancel out. So every charge DQ has a mirror image such that the vertical components add up, but the horizontal components cancel out. So all I need to keep as I go around the ring is the vertical component of the electric field, and then add up all the contributions to get the total field. I don't have to add up all the horizontals, because if I did, in the end, I'm going to get a 0. So I go through the math just to get a 0 when we can exploit the symmetry from the beginning and just not worry about the math. Okay, so from symmetry, you know, DE horizontal, yeah, you know, basically cancels out. So we only keep DE vertical. Okay, so this DE right here changes now to DE vertical, which is DE cosine alpha. Almost done. We just need now to start plugging things in, but let's see what cosine alpha is. Let me draw a triangle right here. Again, if this is alpha right here, then this is alpha right here. But let's draw a triangle so we can see it better. Here's alpha, here's Z, here's capital R, the radius of the disk is little r. And here at this point is my dq with a little length dl. So from the trig, cosine alpha is just Z over R. But the problem was not given in terms of R. I only have Q and I have capital R and Z and maybe lambda. I'd rather put everything in terms of Q. Well, I need to get R in terms of known quantities. So looking at this triangle, I can tell that R is the square root of capital R squared plus Z squared. So now cosine alpha is Z over that square root. So let's go down here now that we know what R and cosine alpha are. So now dE, there's the dE up here, K lambda dL over R squared. And cosine alpha is Z over R. These R's combined to give me R cubed, K Z lambda dL over R cubed. But remember, R was the square root of capital R squared plus Z squared. So R cubed, which is basically R squared plus Z squared to the 1/2 power. So R cubed, we just multiply this power by 3. So it's K Z lambda over R squared plus Z squared to the 3/2 times dL. Now this is my element or infinitesimal electric field. So all I need to do now is go around the circumference like this, starting maybe from here, and go around the circumference and add up all these contributions coming from these little dLs. Okay? And each dL is giving me this much contribution right here. So now the electric field in the vertical direction, again, these are all constants. K is the constant from Coulomb's law. Z is a constant because I am at a fixed height above the center of the ring. Lambda is a uniform charge density. R is the radius of the disk. Here comes Z again. So these are outside the integral. We don't care about messing with these inside the integral. The only thing that changes is that I go around the circumference and adding up all the little elements, dL. Well, when I go around the circumference, adding up all the little elements, what do I get? What's the length that I accumulate by doing that? I accumulate the circumference, right? We can put it here from 0 to 2 pi r if you like. But since we're going a full circle, these limits are not needed. I know when I add up all the little lengths across the circumference of a circle, I'm going to get the circumference of the circle. So this is going to be kz lambda 2 pi r over r squared plus z squared 3/2 power. And what is lambda times 2 pi r? Remember, the charge Q was uniformly distributed across the circumference of the ring. So the Q is lambda times the circumference. Okay. So this here, lambda times 2 pi r is Q. So basically E vertical is KZQ r squared plus z squared to the 3/2 power. And again, this is in the z direction. vertically up. So this is the electric field, a point Z above the center of a ring. And it doesn't have to be above, right? I could have a ring like this, of radius R, and I'm a distance Z away from the, along the axis of the ring, and a distance Z away from it. Here's point P. This will have the same magnitude, the same quantity, but it will be in, like this, to the right. Okay? And if the charge on it is negative, the electric field will be to the left. But the magnitude is here. And this Z is the distance from the, along the axis of the ring, above the plane of the ring. So now, is this a good answer? One last thing. One way to find out in some of these problems is to basically go stand a distance far, far, far away from the ring. And when we do that, the ring will not appear as a ring anymore, right? Take a ring, a ring that you put on your finger, and put it, say 50 feet away from you, or 100 feet away from you. It will not look like a ring anymore. You probably cannot determine that it has a radius. You'll probably see it like as a dot or as a ball, just like it will not be a point charge, but it'll be like a little mass, but no discernible radius. Now imagine going really far away from it. Look at the stars, right? Some of the stars in the sky are bigger than our sun. And yet when we look at them, we see point sources of light. So the farther away we are, the objects will appear like a point source. So from this, for this ring, if we are a distance close to infinity away, in other words, as Z goes to infinity, or another way of saying it, Z is much, much bigger than R, radius of the ring, huge amount, then we should see a point charge. Does this equation reduce to the electric field of a point charge a distance Z away? Well, let's see. Since Z is much, much bigger than R, then R squared plus Z squared is approximately, we can say approximately Z squared. Again, Z is going to infinity. I'm so far away from the ring. So now what's the E vertical? KZQ over, now R squared plus Z squared is Z squared. Z squared to the 3/2 is Z cubed. These simplify, KQ over Z squared, which is the E field, a distance Z away from a point charge, Q. So this one checks out. Most likely this one is a good answer. And this is the analysis. So in the next video, I am going to use this result to compute the electric field of a disk of radius R, where there's some charge distribution on the disk. Basically, our charge Q is spread equally across the disk. So we'll be talking about surface charge density, uniform, and we will try to use this result to compute the electric field above the plane of the field along its axis. All right, I hope this was informative, and I will see you in the next video.